Okay, so we're going to go through these definitions quickly. You won't probably have time to write them down. I would say get them off the classroom later or print it out. It's not probably worth writing them down. You can just access them. You don't need to know formal definitions, but you certainly need to know what an asymptote is, and you need to know some of the technicalities of when different kinds of asymptotes occur. So, you want to be able to reference these definitions, I suppose, just as you're reviewing that material. We're just doing some work recognizing some characteristics today. It's actually pretty straightforward. Notice a couple of interesting things, but then on the next class, we're going to use these concepts to start graphing. Okay, so eventually, that's our goal. But today, we're not doing any graphing, no sketching yet. So vertical asymptotes, we have certainly seen these before, as well as horizontal asymptotes. We know when vertical asymptotes occur already. Again, here's your kind of formal definition: infinitesimally closer, but never touches. They are of the form x equals a, so that's what a vertical asymptote, that's how we describe one. We state its equation. And a corresponds to a 0 of the denominator of the function. So any value that would make the denominator of a function equal 0 is where a vertical asymptote will occur, which means that our function that we're looking at has to be written in a proper form where we can determine where a 0 would be. Horizontal asymptotes. Okay, so again, you have seen these before, although we haven't talked about them as much. They're of the form y equals b, and b corresponds to a y value. We're going to look at this in a minute, where the function has no value. So somewhere where you plug in an x, but it doesn't give you a y value. The y value is not attainable. So let's say, for whatever reason, the function doesn't resolve ever to 5, right? So no matter what x you put in, you can never get the value of 5. That's where there's a horizontal asymptote. We'll see what that means in a moment. And these only occur, so this might help you a little bit if you can keep this in mind, when the degree of the numerator of the rational function is less than or equal to the degree of the denominator. I'm not sure that you memorize that. It's going to, for the most part, be fairly clear when there's horizontal asymptotes, I think. But there's a couple of tricky little kinds, so if this might be worthwhile sort of remembering, thinking about as you're doing this. Next one, something we haven't seen, oblique asymptotes. We're only going to see them a little bit. So this is a straight line. It's not horizontal, it's not vertical. But the function still approaches this line infinitesimally closely and never touches it. So regular asymptote, but it's oblique. It's also called a slant asymptote. So in other words, it's like a slanted line, not horizontal and not vertical, but is otherwise an asymptote. So these would be of the form y equals mx plus b. You'd have to have the actual equation of a line in order to describe one of these. And these only occur, this is important, so this is something you just need to know, when the degree of the numerator is exactly one more than the degree of the denominator. Okay, and that's when you get an oblique asymptote. And then whole in a function. Again, we'll see what this means in a minute, but this occurs when there is a common factor, a particular type of common factor between the numerator and the denominator in a rational function. Okay, so I would, after we've gone through the rest of these examples and you've done a little bit of this, you could go back and read these definitions again, and then it might kind of solidify them a little bit more for you. So let's take a look. Example 1, all we're going to look for is we're going to take a look at what a whole looks like and what vertical asymptotes look like very simply. So the first example, give you a second to write that down. But the first example is not in the right form to determine where vertical asymptotes would be. So let's just fix that. X plus 3, x plus 4, right? We want it in factored form so that we can tell when the denominator resolves to 0. And so now we have to say whether it's a vertical asymptote or horizontal asymptote or what we're saying. So I'm going to say the vertical asymptotes now. X equals -3 and x equals -4. Those values of x will make the denominator 0. There is not, there is a horizontal asymptote. So, but we didn't need to do that in this one. Yeah, so we're going to talk about that in the next example after we do another little activity. So this one does have a horizontal asymptote, but it'll make more sense where it is and how to find it in a moment. And a hole, no holes. So that one's done. That's easy. The point of that is you got to factor the denominator so you can see what's happening. The next one looks pretty straightforward. You guys did a great job of this the other day, recognizing that the top is not factored. And so when I factor it, something different maybe is noticeable, right? So this is the kind of common factor, like a constant common factor. If I had a 3 on top and a 3 on bottom, that's not going to give me a hole. It's when a common factor is like a rational factor, involves x. That's the kind of common factor that we're looking for that gives the graph a hole. So this, and we talked about this with rational functions. This is exactly where it comes back to. Let's see what this means. This means that the graph of this will look like that. And you know a lot about what that looks like from grade 11 and from what we've done this year. 3 over x plus 2, we can graph that. That's what this graph will look like. However, that's what the original graph up here, will look like. It'll basically look like this, except that at x equals positive 1, it won't look like that. Because the original graph, if you put in x equals positive 1, you get 0 over 0. Well, that's not a value. That's not 0. Please, I hope you don't think that's 0. That has no meaning in mathematics, 0 over 0. So the graph doesn't look like anything there. And that's what a hole is. And so let's see, our vertical asymptote occurs we only have one when x equals negative 2, because the other possible asymptote, I suppose, would have been that factor, but it is actually a hole. Okay, so a hole at x equals positive 1. Okay, it's not a line though, so this is maybe a minor detail, but notice that this is a line. I said at x equals 1 because it's a hole. So this one is like the equation of a line. The asymptote is a line, and this one is at the value when x equals 1. There's a hole. Slightly different. But technically speaking, those are two different things. And in mathematics, sometimes it's important to be technical, as all of you know. Okay, so that's that. I don't think we'll take a look at those graphs because we're going to take a look at some different ones in a moment. So hopefully we're good with vertical asymptotes and holes. We've seen a little bit about what that looks like. Okay, so now let's take a look at horizontal asymptotes. This is a little bit different. The vertical asymptotes, it makes sense. And then in the next class, when we start graphing again, you'll see we're going to look at behavior. We talked about this the other day, but we're going to look at behavior around asymptotes, and we'll see why an asymptote, like why when the denominator is 0, why that doesn't just make the function not exist at that point, but it makes an asymptote as well, because it always will. So that'll maybe be a little bit more clear. If you think about what we did in the previous day, graphing reciprocals of functions, not just the reciprocal function, but looking at reciprocals of functions. If you think about that, that's sort of the lead into why asymptotes exist the way that they are. But when we start sketching these, it'll make some sense then too, right? So then you'll have a bit more of an overall picture, and we'll get that. So horizontal asymptotes. So this is not something that we're going to do. We're going to mess around a little bit here. We're just going to sort of experiment and explore and think about some things. And this is not the kind of thing, the math we're about to do here is not the kind of math that you're going to have to really worry about. But we're just going to try to notice something. And then in the end, our conclusion is pretty straightforward. If I wanted to determine what value of y, remember we talked about this before, somewhere where this function right here doesn't resolve to anything. So some value of y that you can't get. I put in some x, and I don't get a value for y. It just doesn't work. So there's no way of getting that value for y. There is no x that can give me a particular value of y. What value of y is that? That's what we're going to try to figure out. So let's assume, we do this a lot in mathematics, it seems strange, but let's assume this value is y, okay? Or sorry, that the value for y is a. So a is the value that we can't get. Now what I'm going to do is I'm going to take the denominator and multiply it over on the other side. Okay, so that's going to end up being a times x plus 2 equals 2x plus 3. And that's going to give me ax plus 2a equals 2x plus 3. Now here's where we can look at this, and I can sort of think to myself, just by inspection, what value, so I want you to think about this, see if you can come up with something. It might seem tricky, but if it clicks for you, it's actually not that bad. What value for a, pick any value you like, but will this function not work out? So think about this. I'll give you a little tip. If I put in 10 for a, this is going to be 20, right? So this part here will always be some constant, because a is a constant. A is just a number. So that will be a number, okay? But a will be the coefficient of that term. So what coefficient of that x term do I want such that this entire linear equation, doesn't make sense, doesn't work? So what do you think? If you're not sure, you could try a few things. Try 5 and see if you can solve it. Try 8, see if you can solve it. Try -1, see if you can solve it. So if you picked 2, what happens? We get 2x plus 4, 2 times a is 4, equals 2x plus 3. Subtract 2 from both sides, and we get 4 equals 3. Aha. So that value, when the coefficients are the same, it doesn't work. So when a equals 2, so that means that we can't get a y value of 2. We tried. We did it by inspection. We didn't calculate anything. We did it by inspection, but we're noticing now that it doesn't matter what x I put in, I'm not going to get a y value of 2. Because when I try to put in a y value of 2, the x's just disappeared. Aha. Okay. So, so in this case, my horizontal asymptote occurs at y equals 2. But we probably don't know how to use this yet, so let's take a look at another example. So how about this one? We're going to do the same thing. We're going to let a be the value where it doesn't work. 3x plus 1 over 2x plus 5. Again, I'm going to move the 2x plus 5 over, and I get 2ax plus 5a. That part doesn't really matter, right? The constant part doesn't matter. So 5a, that part's not really going to be relevant. It's the x coefficients and the x parts that we're worried about. So now we know, hopefully we know, that I need, in order for it not to work, this has to equal 3. And then the x parts are going to be gone. They're going to cancel on either side. So what value of a will give me a 3 over here? And in fact, you could solve this pretty easily. 2a equals 3. Divide both sides by 2. A is 3 over 2. So there you go. So 3 over 2 is the value that is not possible to get from this function. Okay, so our horizontal asymptote is y equals 3 over 2. Now, what do you notice about 3 over 2 and about the original function? 3 over 2. And then here's the next question. Is that a coincidence, or will that always work? Think about that for a moment and convince yourself. That will always work, because the 2 came from the bottom and ended up over here, and I want that to cancel out, so I'm always going to be dividing by the number on the bottom to get rid of it, right? Think about how we solved over there. And I'm always going to be multiplying by that number on top, which is just that number. So it turns out that horizontal asymptotes are quite easy to spot. All of this messing around that seemed kind of strange at first. You know, I don't know, I would never have been able to figure that out myself. Well, maybe, but we did it together. As I said, we were just exploring, and now we found a pattern. And even if you don't quite see it yet, as always, I would encourage you to really go back and think about it. But in the end, using it is quite simple. So let's go ahead and try that. Determine, now we're looking for vertical and horizontal asymptotes, any holes, and if there is an oblique asymptote or not. Again, you don't have to state the equation of oblique asymptotes, you just would always state if there is one or not. Okay, so the first question, x plus 1 over 2x plus 1 times x minus 3. We can do the vertical asymptotes first. Let's do that. So the vertical asymptotes are when x equals negative 1 over 2, and when x equals 3, that's when the bottom resolves to 0, right? Horizontal asymptote, now this one's a little bit tricky. No holes in this one. Where's the horizontal asymptote? And no oblique asymptotes here. Remember, go back to the definition. Oblique asymptote is when the degree of the numerator is exactly one more than the degree of the denominator. In this one, the degree of the denominator is more than the degree of the numerator. So that's not oblique asymptote. That's the other way around. But think about this for a minute. What is this? Has a degree of 2. And so the leading coefficient is going to be 2x. If I expanded this, is going to be 2x squared, right? And so we look at and then we think about the top. If we're kind of trying to apply this thinking here, if I look at the top, what's the coefficient of the x squared term in the top? It's 0, because there isn't an x squared term. So it's like 0 over 2, which is 0. So in this case, if you go back to the definitions, you will have horizontal asymptotes when the degree of the numerator is less than or equal to the degree of the denominator. And if it's less than the degree of the denominator, then it's always going to be x equals 0. And you saw a lot of that, except for that one case that you saw a lot of that, in grade 11, when you look at things like, just quickly, y equals, 3 over x minus 1, right? So that has a horizontal asymptote at x equals 0, and that's y. But we didn't think about it like that back then. Now, you probably, if you're really thinking this through, you go, well, what if it looks like this? Well, that's a bit of a different case because it has a shift in it, and we're looking at these in a different form at this point, so that's not the same kind of comparison. But you're right, that a shift does move the horizontal asymptotes. That's not something that we're going to look at really, for the most part. We're looking at these straightforward kind and looking for those characteristics in these types. Okay, let's take a look at this graph. Try not to look at the other ones. Don't get a sense of what they look like. Don't look. So this is a very interesting graph. We will talk a little bit more about these down the road, but it has a horizontal asymptote there at, I think it was x equals negative a half, right? A horizontal asymptote here at x equals 3. And take a look at this, vertical asymptotes, and take a look at this horizontal asymptote at x equals 0. This is really cool. We're going to look at this later. But so it's actually approaching from the top here, but it's approaching from the bottom here. And this is what happens when the degrees don't match. But this one, I'm going to embellish this a little bit. It drops below and then approaches like that. So that's really curious. Usually that's not something we need to worry much about. Usually that's not something that like we don't need to necessarily determine that, but it is something that we can determine. We'll explore that a little bit. Okay, next one. See, if you looked at the graph, it kind of blew it, but it's pretty straightforward. The degree of the numerator is exactly 1 more. It's 2, and the degree of the denominator is 1, so it's exactly 1 more than the degree of the denominator. Now we still have a vertical asymptote. Whoops. We still have a vertical asymptote when x equals 0, because the bottom does resolve to 0. But this also has an oblique asymptote. Okay, and that's it. How do you find the oblique asymptote? It's actually pretty easy, but it's not something we're going to worry about right now. Easy for us because we have the skills to do that. Okay, this one I think is pretty straightforward. So it has one vertical asymptote when x equals -1/3, and it has a horizontal asymptote. So this is when we apply that stuff that we did. I'll give you a second here to see if you can figure it out yourself. It's of the form y equals, and it's 2/3. And why is it 2/3? Because of those coefficients. That's all there is to it. Coefficient of the x on top over the coefficient of the x on bottom. And then, let's take a look at those two graphs now that we've done it. So that's what an oblique asymptote looks like that. And you notice that it doesn't have a horizontal asymptote. Not that it's impossible to find a graph that doesn't have both, but the ones we see in this course really won't. You can think about it one way, where a horizontal asymptote, if it did have one, happens where the two, like the oblique kind of takes over. But if you think about what we had talked about before, it doesn't really make sense to have a horizontal asymptote, but does have a vertical asymptote. In this case, it was at x equals 0. Okay. And then this is the next one, so it's pretty straightforward. It has one vertical asymptote and one horizontal asymptote. Okay, and those were at y equals 2/3 and -1/3. Hard to tell from the graph that those are exactly where those are, but it makes sense when you think about it. Okay, and then the last one. So what do you think? Looks a lot like example C, but hopefully you're not fooled, and you see that there is a common factor on the top, as well as a common factor on the bottom. Whoops, not 2, sorry, 3. And so these divide, and the simplified version of this is y equals 2/3. So I'm glad we didn't get a peek at that graph. What do we expect it to look like? We expect it to look like the simplified version of the expression. That's what simplifying rational expressions is for. We talked about this in the previous class. They are equal. What does equal mean? It means their graphs of those functions are identical, except there's this restriction where x can't equal -2, because at -2 it doesn't equal this. Right? It looks like something else. What does it look like? Well, in this case, it's a hole, because it doesn't make sense to have 0/0. But otherwise, the graph does look like a straight line. There you go. And there's the hole when x equals 2. Now, just FYI, this graph was created in GeoGebra. GeoGebra doesn't automatically recognize holes. I had to put the hole in there, make it look like there was a hole in there. GeoGebra won't do that. So if you graph these and you look for a hole, you're not going to see it. You have to calculate those holes on your own. There may be other software out there, but I'm not sure. There's not really that I know of that identifies holes that way, like graphically. Okay, but you will be able to see asymptotes. You will be able to see oblique asymptotes and horizontal and vertical asymptotes when you graph it. So again, I encourage you to be visualizing these, graphing them and visualizing them, and sort of double checking that they make sense. And we're going to start doing some graphing and sketching. So then, for sure, you want to be absolutely sure that your graphs look like what they're supposed to. Okay, and there's no horizontal or vertical asymptotes in that graph in particular. You can have graphs with holes and vertical and horizontal asymptotes, but this one, it doesn't have that. Okay, page 262, 1 to 3 is your practice, and good luck. And make sure that you can do this stuff so that we can start using it to do some sketching next class.